Hi, you're welcome to our Day 4 coding section. And in this coding section, we'll be looking at baseline modeling using linear regression and random forest. So let's dive in. The first thing you need to do is to open a new Jupyter notebook. And if you want to have access to this material into this class, please look out to my GitHub, which you can find in the description. So the first thing we need to do is to rename and give a title to the script. So we're just going to call it Day4 Baseline Model. So we'll be covering just two models, the linear regression and the random forest. Now you could guess what we can do first. The first thing you need to do here is to import libraries. So which libraries do we want to import? We import pandas as PD, which helps for our data manipulation and analysis. We are going to import NumPy as NP, which is going to help us for the numerical computation. We are also going to import matplotlib .pyplots as PLT. We have to shorten the name for reusability. So this matplotlib will help us create visual plots. And next, we are going to import Seaborn as SNS. So this is just the higher level visualization library built on top of matplotlib. Next line of code, once you're done, you can run. So next line of code will be for us to split data and model inputs. So what we need to do is to start from skyscattering, which is the inbuilt ML toolkit. So we have skyscats represented as sk.len, that's model selection. From here, we are going to import the train test split. So this train test split function is to split our data into test and training sets. Another import we are going to do from skyscattering pardon, there's no dots here. That's a typo. We're going to import linear regression from skyscattering.linear model. So we are going to import linear regression. Kindly take note of the capital L and the capital R. So this imports linear regression, which is the basic model that assumes a linear relationship between inputs and targets. Next will be from skyscattering that ensemble. This will tell you that we're talking about the random forest. Yes. And remember I told you why it is a symbol model. In case if you want to know more, make reference to the Day4 lecture video where I gave the theoretical explanation of the baseline model. Okay, so once we are done with this, this particular line of code, import random forest, is an ensemble method based on decision trees for robust prediction. And we're going to import the evaluation metrics. And we are going to see from skyscattering that metrics. We are talking about the evaluation metrics, so take notes. And recall, if we're talking about evaluation metrics, we are talking about the mean square error, the mean absolute error, the RMSE square error, the R square, shortly known as MAE, MSE, RMSE, R square. Yeah. So let me write that out. First, the mean square error, the mean absolute error, and the R square error. Okay. Oh, so this line of code is going to install, import, sorry, the evaluation metrics, the MAE, the MSE, and the R square. You could also put the, okay, don't worry about that. I'll show you something, what we can add to get more metrics, like the RMS square. From M, for mean square error, you can get the RMS square. So I'll show you a code to add to get the RMS square from mean square error. So let's move to the next thing. You run this, no error. So we move on. Next step is to load and prepare the dataset. Assigning df as the variable, we are going to load the dataset into it. Here we are going to have df is the variable. Here we are going to have PD, which is pandas read underscore CSV. So we are going to read the dataset. Could you remember where this dataset is coming from? So if you started with our day 2 and day 3, where we did the EDA and the feature engineering, you could see the step-by-step process on how we were able to analyze our data and then save our data. So we are using the data after the processing using the feature engineering, which we have renamed as features, yeah, with the format, CSV format. Yeah. So if you are joining us to do this coding, you could download the dataset from my GitHub, the process dataset, yes, called features. Having loaded the datasets containing the feature engineered values from a CSV file, the next thing we are going to do, we are going to drop the target and the timestamp column. So what do we use to drop? We are going to use df.drop. Why df? Because the dataset has been loaded into df. So we have to call df.drop. So drop function enable us to drop a particular column we don't want. So in this case, we are dealing with column. It could be rows, it could be column. So we are indicating the column as equal to, in a square bracket, you put the text of that column you want to drop. So be specific with the name, else you get error. So we have the global active power as the Y target. And then the the date time, sorry, which is the combination of the date column and the time column. We are also dropping that. Okay, so you could have a quick look at your code to see if everything is okay. So once we have represented that with X, we are going to use Y for our targets. So we have DF to represent our targets, which is the global active power. Okay. Yeah, so this defines the attribute target variable Y we want to predict. So just run the cell. Correct. So we go to the next step. So in this step, we want to have the train test splits. So I mentioned in the video 2, machine learning overview, once you've processed your data sets, the next thing you need to do is to split your data sets. You have a choice of what your split ratio should look like. You could use 70, 30, 85, 15, 80, 20, 10, 90, 10, however it is. But just be careful to try different splits so you can come to a best prediction outcome. So in this case, we are going to assign the train test splits into 4 variables: the X train, the X test, the Y train, the Y test. Remember, supervised learning has to do with what? Input and label. So that input and label is going to represent our X and Y. Now, representing our X and Y, it means we have to have X train, Y train. Then to test that data, we are going to have X test and Y test. I hope you understand. So let me write that out so that you can understand. So we are going to have big X. So whatever you want to present it with, the reason why I'm giving big X is because of this variable I represented it with. So if you have small x here, it means you're going to use small x here. Okay, so we have big X, the test, and then we are going to have Y train and Y test. So using what? Using the train test split function. So what are the parameters in train test split function? We are going to first of all have S, which is the X future data. Then we are going to have Y, which is the target value. Then we are going to have the ratio. That means what are we splitting the data into? How are we splitting the data? So if you see 0.2, it means 20%, 20 divided by 100, which is 0.2. So what does that literally mean? It means that we have 2 million data sets. So we are using 2 million plus data sets. So we are using 20% of 2 million for testing and 80% of 2 million for training. Yes. So let's see, shuffle, false. So we don't want to shuffle it. So we set it as false. Okay. I hope you're able to understand this line. I just want my coding section to be something simple you can understand each line, because it's very helpful when you can understand every line of code. Okay, so let's go to the next thing. After you split the data sets, the next thing we will need to do is to, okay, once you're done here, you can run. The next thing we need to do is to call the model. So in this class, we're using the regression model, specifically linear regression and random forest. If you check my lecture, Day4 lecture, I explained different types of regression model, but in this practical section, I'm just focusing on 2. For stretch exercise, you could actually call those other models, and definitely it's going to work. I'll just give you an general view how you call models and see how it works. For instance, let's look at linear regression model. For us to call that, it means that I have to initialize the linear regression model instance. So I'm using that as OLS, or calling the linear regression. Okay, so once you're done with this, the next step you're going to do for the linear regression is to fit the model on the training data. We have to train the data first before testing the data set. So how do we fit the model on the training data set? All you need to do is to say OLS, which is this you're calling, dot fit function. Now in that fit function, the next thing you need to do, you need to specify what is the train data? Now, the train data has to do with the input and the label. So our input is X and our label, our input is X. Yes, our label is Y. So we have big X train, comma, Y train. Good. This is looking so simple and interesting. Yeah. So the next thing we need to do is we are going to use this train model to make prediction on the test set. What that literally means is, for instance, if you're in a class and you go for lecture, what do we do in school or university or high school? All you need to do is you train the students and then you assess the students. How do you assess the students? You assess the student based on what you've taught them. Simply what machine learning is trying to do. Machine learning has trained the data set and trying to test the data set to see the performance. So in this case, we are going to have Y spread, which is predicts, OLS as the variable. Here we are going to use OLS that predicts. This is going to predict. Remember, this is going to fit, but this is going to predict. This is doing training, but this is doing testing. So we are going to have what? X test. Yeah. Okay. So we are done with this. So let's run the cell. Good to go. Our next in line is for us to work on the second model, which is the random forest. Now, random forest is quite different in terms of the parameters we want to put. So in this case, we are just calling it the default linear regression. Let me show you for random forest where we can input some parameters inside. So let me just copy and paste to be a bit faster. And this case, we have RSF to represent the random forest. And we have here random forest regressor. Running through the number of estimation, we will have n estimators set as 200, comma, we're putting the random states at 42. Sometimes you could use random states being 0, so you can try. Having done this, this is going to initialize the random forest with 200 trees, random states 42 to ensure reproducibility. Yes. Okay, so let's train this. I'm going to chain this as rf.fit, the same X train, Y train. We're still using the same data sets because we want to compare the results for linear regression and random forest. The same thing in real world application. You can try different machine learning models to see which performs better for your given data sets. You don't just rely on one machine learning model, never. And remember, even that your data set has to be processed for you to get a good result. Next, we have our RF predicts. So I'm erasing the OLS to change to RF. So we're done with this and we run. Okay. So next is we have to provide the model evaluation function. So in this case, we are going to define a function to print the mean absolute error, the root mean square error, the R square error. You could also do for the mean square error. So all we need to do is to define print underscore matrix. Here we are going to put our Y true, Y predicts, and the model name. So we have here print. Let's set dot dash. So 3 dash, curly brackets, model underscore name, close it, space, dash, this, and close brackets. And we'll do the same for prints. This mean absolute error, curly brackets. Now we are going to, for absolute error, so we are trying to put down the mathematical calculation, okay? Y credits, and we are finding that whatever value is going to get, it's going to set it as 3F. It means 3-dimensional places. Okay, so we are done with this. I could as well copy this and paste and just make few modification. So if I'm dealing with RMSE and MSE, so all I need to do here is to call this one squared error. And okay, so let me change this to 4F so you could see the difference. And let's say this is RMSE. That is the root mean square error. So for root mean square error, if you remember the formula, it has to do with the square root of root mean square. So we are going to call MP as the numerical computing library dot sqrt, which is the roots, square roots, and brackets roots squared error. Okay, so we have that. And last but not the least, we have R squared, which is going to be R squared score, R2 score, which represents R squared. Y through Y predicts, give us in this, and a new line. So take notes, C is missing here in the matrix. Okay, so we have Y predicts, Y through Y predicts, the 3F. I'm just trying to cross-check mid square error, Y through Y predicts, setting this as 4 decimal place. NP square root mean squared error, Y through Y predicts, and then the R score, Y through Y predicts. Okay, so we are going to run this. RF is taking longer time, so if you don't want to waste your time, you could reduce the 3 to 10. So I'll come back here if it takes a long time. I'll just change this. I could just come to the kernel, restart, and change this to 10. So, but let's continue. Let's see how much time we need for that. Having done this, we are going to print the evaluation matrix. So here is to print the evaluation matrix. To print the evaluation matrix, we are going to have print matrix y test y pred, which is to predict OLS. So we have OLS to present that. And we are also going to do for random forest. So let me copy and paste. So this is for RF. I haven't done for OLS. We're going to do for random forest. I find coding section very interesting. I don't know about you. So once we are done with this, the next thing we want to do according to our lecture is to check the scatter plots, where we'll be looking at the actual and the predicted. So we are going to set the plot size and do many more. So let me just code it so that you can see. So because I don't have so much time, I'm going to change this to 5 or to 10. Okay, so whichever choice you want. So I'm going to restart and run it again. So this can move very fast. Okay, so let's see this for the scatter plot. Like I said, if you want to plot, all you need is matplotlib, which we have represented as PLT. So we will have plt.figure in brackets. We're going to indicate the size. So we want to set it as 6 by 6 inches. So we are going to indicate that as 6,6. So we'll be able to set the plot size to 6 by 6 inches. Next is to plot the actual versus predicted value as a scatter plot with transparency. So we are going to say plt.scatter in brackets y test, y predicts, alpha 0.3. And we have plt.plot brackets we have y test dot meaning, that's minimum, comma y test also just a moment, we have an error here. So it said something is missing. F string closing parenthesis does not match opening parenthesis. Okay, so we have F RMSE mp.sqr this. Okay, y through. Okay, so we are supposed to have 2 brackets here. Okay, so this is to close this is to close this, and then this is to close this. Okay, so let's see again. So that's correct now. So let's see why it's not defined. Yeah, so remember we did not change this RF. So you run again. Never be discouraged when you have an error. It's part of the training. It's part of the training. Okay, so let's see again before I continue this line of code. Oh, so while we are waiting, let's continue. So we have y test mean, comma y test max dot max, okay? Y y test mean, y test max, then r dash dash. Now you'll be wondering, what does this mean? This mean red color and the kind of line we want to have. We want to have this kind of line, dash dash line. Okay. Oh, perfect. So we have our results. MAE 0.0, MSE 0, RMSE 0.001, R square 1. Almost the same. The same. Yeah, so it shows our model is perfect. Oh, cool. So could you see the difference between 3F and 4F? So that tells us 3 decimal places and 4 decimal places. Okay. This is nice. Very nice. Very nice prediction. Now you're going to visualize why I said this is nice once we are done with the actual and predicted scatter plot. So let's see what's next remaining. So like I said, I'm adding a red dash reference line indicating perfect prediction y equals to x. So let's go to the next thing. We are going to add label, title, and show the plot. So let's see that. plt.x label is going to handle what we should write on the x-axis, the title for the x-axis. We're setting that as actual. And then for the y-axis, it will be plt.y label. In brackets, we have predicted. Okay, so next we have plt.title. In brackets, we're going to give any title you want. So I'm just giving it as Random Forest actual versus predicted. So don't forget to give that the quote sign. And then PLT is to show us the plot. So if you don't want to use PLT, if you want to close it up, you just say plt.close. Okay. Now, could you guess why I named my title as Random Forest actual versus predicted? Why didn't I call it OLS? Now recap. You could see here I was referring to RF using the Y predicts RF. So if I'm to draw for OLS, I'm going to put OLS here. So take note of the difference, just like what we have here and here. Okay, so let's run that and see. Okay, so another error. So I'm having the error towards here. So let's see bit by bit. Okay, so here I'm supposed to have a square bracket. Why okay, so let me run it again. Yeah, perfect. So you can see why I said this is a perfect graph. So absolutely, we are having y equals to x. This is a perfect graph. So when you see it's not being a perfect graph, is when your predicted is very far apart from the actual value. Like maybe we have it all over the places here. It's not fitted within that R dash dash mark. So that is where we can say we are having poor prediction, but this is absolutely a perfect prediction. Okay, so would you like to try for OLX? All you need to simply do is put this and definitely change this to OLS, and you can call this linear regression. Okay, so maybe we can change this to green. Yeah, so you can see for linear regression. So you can see that. Nice. Okay, so let's look at residual plots and then go into feature importance. So for residual plots, we're going to have PLT dot figure, peak size. This time, let's change the value to 10 by 4. And the PLT dot plots, we want to plot residuals and we put the values. And then we kind of put our horizontal line, which is dot AX H line, where we say y equal to 0, comma, set the color as red, represented as R, and our line style, we want to use the hyphen. Then we close our brackets. Go ahead to put the title, the x-axis label, and the y-axis label. So let me just copy from here and quickly modify. It's not my intention to make this code section lengthy, but I just have to explain what each line cell represents. What does it mean? So at the end of the day, when you see this line of code, you can be able to tell the meaning and never being afraid. So here we have residual and pip just show. Okay, so let's run this. Now fixed size not defined. Oh, I didn't put equal to. Okay, so let's see again. PLT dot plot is not supposed to have X. Okay, and the residuals. Okay, so I'm supposed to define my residual. So at the beginning, I'm going to define my residual as the mathematical calculations of the difference between the Y tests and the Y predicts for RF. Okay. So we are having this. Perfect. So let's see the feature importance. So I have a task for you. If you want to do for OLS, what would you do? So let me know in the comment section, but I can give you a tip. Look here, you're going to change something here. Yeah, so just quickly look at what we have here. Yeah, what we have here. So that is what you use to replace here for you to plot the residual for OLS. Next is the feature importance. So let's consider the feature importance. Let's put the mathematical calculation, which is features equal to, we are assigning that to the variable importance. So let's see what we have here. Our feature underscore features. Yeah, so this line of code is going to extract the feature importance values from the trained random forest model. So next we need to do, with this variable feature df, we are going to call our pandas data frame. And lovely, we are going to call the parameters we need here, which includes the future, which equals the X column and importance, looking at importance. Okay, so just 2 parameters inside. And the curly brackets. So we have P underscore DF dot values. Okay, so we are working with the importance and in ascending order, we say false. And in place, we set as true. We'll go back again with a big size, the title, the bar plot. So let's, and the seaborn code. So we have PLT dot figure, setting the fig size as 10 by 5. And this time we're using seaborn, looking at bar plot. So we have importance, Y, which has the feature this is supposed to be S, not Z. Then the data, which has the feature difference, feature data frame. Then set your title. We have plt.title. The title we're going to give is feature importance. And plt.show. Okay. So let's see this. Run if there will be any error. Yeah, so we can see the future importance. We have the apparent power, the global intensity as the 2 valuable features, 2 important features. Okay, so you can see that we'll be able to visualize the importance of each features using the horizontal bar plots. Okay, so maybe you'll be wondering, why did we use the data frame? So this data frame is just to create data frame to rank features by their contribution to prediction. So that is what we can see here. So in summary, this notebook implements importing the libraries, calling the data sets, doing the data split and preparation, using 2 baseline models, which are linear regression and random forest, calling the evaluation metrics, which are MAE, MSE, R square, RMSE, and also going through the visualization, like the residual and the prediction. And lastly, we consider the feature importance interpretation. So this is all we have for the Day4 coding section. Would you like to see more of this lecture? Lo and behold, we have our Day5. We'll be looking at XGBoost, which is one of the best gradient boosting model. Watch out for my day 5 lecture and my coding section in this YouTube channel. Don't forget to like, share, subscribe, and hit the notification bell so you get notified when I release my new video. Thank you for watching. I'll be signing off now. Have a nice time. Bye.